Hello everyone. Are you able to hear me? Okay. All right. Hey, my name is Kumar. I'm a computer scientist at University of Alabama in Huntsville. I work closely with a NASA project called NASA Impact. So I'll be presenting most of today. So the first presentation is supposed to be given by Manil Maskey. He's my manager. He's a senior research scientist in NASA Marshall Space Flight Center. Unfortunately, he cannot make it to Santiago today. He was here last time, but right now it's 2:30 a.m. In the US, so I don't want to have him present. So I'm going to try and cover this part of the slides for this time. So before moving forward, I want to thank Dora and Gabriella and everyone involved in the HDCRS for the opportunity to present and the hands-on and organizing the summer school. So it's a really cool opportunity. So thank you. So the goals for the summer school is building capacity around data science and with a focus on computing. Obviously, to explore research and applications around foundation models, specifically for Earth observation. We built a few different foundation models. We started with Earth observation, but we are moving slowly towards other areas of foundation models in science, specifically NASA science. But we start with observation, which we will be covering in the hands-on field today. We also want to provide some hands-on experience, which we will cover later today in to support the science research life cycle. Specifically today, we'll use some cloud computing platform resources, AWS, to fine-tune a geospatial foundation model and also to deploy and infer from a training model. So it's going to be a different flavor to your typical HPC or your typical like a training notebook, I would say. So we also want to provide a forum to exchange ideas and enable collaboration here as well. So feel free to ask any questions and open discussions. So a brief talk about the science research lifecycle and how we do AI within NASA and data management. So, a science research lifecycle starts with an observation. That observation leads to a question, and from that question, we need to form an hypothesis. An hypothesis necessitates forming an experiment to understand or answer to explore that hypothesis. And that experiment needs to be contextualized by some analysis, and that analysis leads to conclusions, and that conclusion leads to further observations, and that's a scientific research life cycle. So within NASA Earth Science, within NASA Earth Science data management specifically, it's a very you can see a similar pattern of observation, question, hypothesis leading to a conclusion, right? So the way it evolves in this case is that we start with a mission. A mission leads to observations and we produce products from the missions. A mission is a satellite mission that we send out and they produce products from them. And those products need to be ingested and stored, and they also need to be documented properly. So this is the starting phase. And these these documentation help facilitate the discoverability life cycle, and they also lead to distribution access of the said products and user support and archive of it. So if the pattern appears here as well, in the sense that you can see there is document generation, cataloging, and using APIs and tools and publishing those tools and services as well. So the point is, within each of these tools and services and that we enable, there is infusion of AI that will help make these services more efficient. So, for example, document generation can use AI, and keyword can enable better documentation. And data cataloging can use AI and language systems to make discoverability and usability easier. Better archive will lead to better downstream applications and building models and so on and so forth. So data management really is a key driver for us to do better AI, and that's a good segue into AI models for today's talk. So starting with supervised learning, there is obviously we all know this paradigm. We start with curated labeled data that leads to model training. We see if it's feasible or not, and then we go forward with more labeled data if it's not, and then iterate it multiple times, and then we finally deploy a model once it's ready, right? So it's your traditional run-of-the-mill training. And we also, there's obviously domain shift that we need to understand and analyze, and then we need to loop it back to training the model. So it's a cycle of constantly updating the model based on changes and observations. So it's your traditional supervised learning. On 2020, around 2020, we saw some patterns emerging, right, in supervised learning. Training data is the main component and the driver for supervised learning, and is also very expensive. It's a bottleneck to advanced applications in machine learning, and geoscience models must generalize across space and time. However, supervised learning needs large training data sets to build generalizable models. So this is a recurring pattern, and they needed hundreds and thousands of data. Back in 2020, we found that this was a bottleneck in advancing AI, and that at that time required a lot of training and manpower. That's why we started exploring into foundation models, and that also coincides with how the industry went. To give a brief timeline, in 2017 to 2018, we saw the Transformer paper that started with BERT, which was a Google's paper, and then around 2020 to 2021, we saw GPT-3, which was the precursor to ChatGPT, which you all know, and so on and so forth. And that was the language model evolution. Vision models took a little bit of a time because of the compute and data requirements, but it did start around 2020 with Clip, which was OpenAI's offering of jointly training language, vision and language, and VIT, which was one of the seminal architectures for foundation models, and so on and so forth. So that was a brief overview of the timeline for foundation models. So what they changed in a paradigm is this, right? So traditional supervised learning needed large labeled training data set, which leads to one ML model, which leads to one application, and so on and so forth for each use case that we have. And that bottleneck, obviously, like we discussed, is in the labeled training data set side. And the foundation model approach, specifically for institutes and data producers, data management folks like us in NASA, We have a large, and ESA as well, we have a large wealth of unlabeled science data sets that we can leverage to create foundation models, which fundamentally uses unlabeled data sets. And going from there to building application, adapting them to applications is lesser, provenly lesser compute and data requirement than your traditional approaches. Why foundation models as application is enticing for us, as a AI approach is enticing for us. Obviously there are multiple approaches. We have zero-shot learning, few-shot labeling, and small label training data set. Zero-shot is where we encode the task along with the input data, so the model understands what the task is along with the data that we provide, and it produces. There are some models emerging. This is more complex training paradigm, and it's still a very new nascent modeling right now. Few shot label is in between zero shot and small shot. We show a few examples in the model labs to it. And most of where we do geospatial applications is in the small training label data set right now, where we see patterns like only provide 10% or 5 to 10% of the labeled data set compared to your traditional supervised learning approach, and the model will generalize to similar performance to your traditional supervised learning approach. It's a common pattern that we saw when we built our first geospatial, or the second version of the first geospatial model, which we'll talk about in the next hour. So that's the overview for AI foundation models. All right. So on the adoption for upstream and downstream, we have not only we are working on, like I said, Earth observation foundation models. We are also building on large language models. And if you go back to the data life cycle that I was talking about, we have the upstream of providing documentations, API access, and assigning keywords to data sets so scientists can discover them easier. So making the data lifecycle easier. There's the upstream part where language foundation models, which are domain specific, are going to help in those areas which are upstream. And then in the downstream areas, we are the idea for making AI, infusing AI is using foundation models it could be on the downstream application areas like classification, detection, prediction, similarity search, and phenomenon detection and all, which is where our foundation models like EO foundation model, weather foundation model, and we're also working on helio physics and other planetary foundation models as well, where it will be. Again, just a brief overview. These are our core tenets. We have established some science goals and data, and we also need to address the compute requirements and the foundational AI expertise that we need to produce in-house, as well as using open collaboration between teams like IBM Research, other universities, and using GRSS and other open avenues that exist out there. So that's where we are heading towards, and I'm going to spend some time discussing HLS foundation model. So again, HLS stands for Harmonized Landsat Sentinel. It's a product that is a harmonization of Landsat, which is a NASA's 30-meter resolution data product, and Sentinel, which is ESA's 10-meter resolution product. Landsat has more bands, like more spectrally high resolution, and Sentinel, not sure how many bands, but I think a little lesser than that. But the harmonized Landsat Sentinel aims to fuse both together with the aim and the idea that you have the best of both worlds is the idea. So the user time is quicker, you have more bands than just each of them together. So just a better of both worlds in a sense. And we have a team of scientists who make sure that the way they are combined is scientifically accurate, and the due diligence is made to make sure the products that are given out is valid and so on. So that's forms the basis for the product, and we use surface reflectance data products. It's the level of the product that we are using for pre-training. We use it for multiple adaptations. For example, we use it for segmentation. Segmentation, which involves tornado tracks, burn scars, flooding, which are some of the use cases, downstream use cases. We use it for similarity search, which is given an image, find similar images. We have a portal for it that we can leverage to find similar images. You can think of use cases where you want to label similar data sets or similar data or find similar data, and you can use this search for it. You can use this service. Then there is classification and object detection, your run-of-the-mill use cases. And image-to-image translation, which is using the encodings from here, we can transfer the style transfer from optical to SAR imagery, which also necessitates there is a SAR foundation model or a way to capture SAR, which we don't have right now. It's just adaptation possibilities right now. Science data product generation is similar to translation, but harmonization with other optical sensors and super resolution using this foundation model as a signal. Right? So the work started off as a collaboration with IBM Research, but right now it is a much larger collaboration, I would say, between multiple universities, JSC, Computing Center, and more. The initial version, the V1, was trained with 100 million and 300 million parameters, and V2 is 300 and 600 million parameters with multi-temporal aspects. We can touch more with the more technical slide, technical presentation after this slide. So yeah, like I said, HLS is a merge of Sentinel-2 and Landsat data, 2 to 4 day global coverage. It's almost seamless daily 330 meter surface reflectance coverage, highly cited data. Total of 2 petabytes have been transferred to users and being used right now. It's currently second most downloaded data from NASA Earth Observation Data Archive, I think, after MODIS, which is probably the most used. You can see how the observation is being made in that video, if it can play. So yeah, this obviously is a 30-meter resolution data product, which is why we have gaps in it, and which is why we have 2 to 4 day global coverage, because we combine the 2 satellites that are doing the overpass. Individually, they have about 10 or so. I'm not entirely sure, but around 10 or more days of individual global coverage. But combined, we get much lesser global coverage. So some application area using this 30-meter resolution for HLS is monitoring fire events, water reservoirs, and snow, active fires, monitor hazards. Land cover use cases are really a good use case to use HLS for. So a lot of value with this particular product. So a few highlights from Prithvi is this is for Prithvi V1. We'll talk about V2 and some highlights later, but evaluated across a few downstream tasks. This showed some generalization capability, which is about 87% less data to meet the same benchmarks at the time of publication, of course, compared to existing benchmarks. Community adoption, it was demoed at the White House with the previous administration. 80 plus downloads from Honeyways. I'm sure that is old information. We have more current information in the next slide. It's part of the ESRI Atlas. We obviously are using it for teaching remote sensing, like this course today. We also did some scaling experiments in Jülich Computing Center as well. We'll talk more about the architecture in the later slide, but essentially it's an encoder decoder block with with a full attention on both the encoder and decoder architectures. Again, I will reserve a detailed conversation later. The sampling strategy also was a little unique in the sense that we made sure all of the climatic regions are covered. The temporal distribution is also made sure to cover all the areas from all the time stamps from 2014 to 2024, which is the full availability of the HLS data product. Some downstream applications are, like I said, burn scar, flood, water, crop classification, cloud gap filling, land cover, land use, eddy covariance, insect damage segmentation, and we have some collaborators actually built a tool monitoring insect damage estimation, specifically locust breeding over Africa. So that was Prithvi-EO. We also did over the last year and this year a Prithvi Weather and Climate Foundation model. To briefly talk about it, this is a grid-free model. It can be used for both multiple topologies. It doesn't really, it's not based on a 2D grid. It's again fully attention-based architecture, tokenization and output projection. It can use convolutions. There is no hard-coded window sizes. We can this can be adapted to any size and any resolution. So it's not conditioned or it's not susceptible to a particular window size. It's invariant to scale is the point. Input data is 40 years of MERA2 data with 163 variables, vertical variables, and you can see if you want to know more about the variables. We added some context information, static inputs like lat-long channels, and vertical climate information like some historical information, surface level information, and vertical data like current data and surface level data as well. So 163 variables of that. And if the variable is time independent, there are 2 timestamps of that. And these dimensions are all stacked together. And this is the pre-training model design for that piece of data. It's on the model level, it's a 2.3 billion parameter model. 163 variables from Meta to data. Again, it's a joint collaboration between NASA, IBM, ORNL, and several universities. This is an autoregressive model trained for forecasting, but also mass reconstruction loss. The decoder can do reconstruction tasks as well. Capable of reconstructing states from partial data and forecasting future states as well. This is not the application area is not focused solely on forecasting. It can also do parameterization, downscaling, and other avenues as well. The architecture is similar. It's an encoder-decoder block, and you can see some samples here. This is a sea level prediction where there is the time frame or the video here shows the forecast, and you can see the difference in the original and the predictions are closer together, but they do diverge slowly as the forecast the window increases. So the delta of error just increases more as the forecast increases. But overall, they do seem to look similar to what the original ground truth is. Some downstream application areas is downscaling, where we take a lower resolution, use upscaling, use this foundation model to condition to make sure that the upscaling happens with proper science conditions, and then produce the high resolution data. Then there is also daily average temperature prediction, which the model also does a fairly good job of predicting. We also use it for wind prediction, gravity wave flux, and high intensity and track estimation also. So that's two of the foundation models. We are also building LLMs, only encoder models. We're not doing decoder models because encoders are more appropriate in terms of data management for data management use cases, and decoder models we are relying on open source or off-the-shelf models with the flavor of encoder models being built in-house, so we can use the domain-specific encoder models, but the decoder models being used. And we're also using building HELIO, Lunar, and so on. So science foundation models as well as within the portfolio. Having said that, the principles are obviously everything is open science. We need to discuss what works, what doesn't, all on the public. Core focus on science and application, early involvement of domain experts. We are involving the science experts as early as possible, right from the architecture and data development stage. So we make sure the model not only captures things stochastically, but also the science, the model is also explainable, and the science dependencies are also captured, and the model is trustworthy. The continuous evaluation of impact and values are also being made. Multi-party stakeholders are because of the inclusion of multifaceted stakeholders, not just us. Aim for extreme transparency, and that you can see by the total number of downloads here, combined, including the data sets and the EO and W, and the LLM, is nearing around 200,000 as of April, if I am correct. So having said that, just a outlook for AI is obviously increasing up until 2023. The pattern looks like it's an exponential increase, but on the foundation models, looks like industry has the upper hand in terms of the number of foundation models being made. You can see Google, Meta, Microsoft, OpenAI, they have the most number of foundation models right now. And this slide explains why. Because up until, let's say, 2010, the compute requirement was mostly on 1.4x a year scale, the gradual increase. And after 2010, I would say we had a much more exponential, a much faster increase in terms of compute because of things coming together like compute infrastructure and so on, hardware cores and so on, that made it much larger, much more capable models. And after 2020, the transformer architecture as well made a lot other highly capable models which necessitated needing large computes and data engineering requirements. So the point being, it's very conducive to industries having figured out all of these things, they can build. They are highly positioned to make these things happen. And researcher having even the world's best GPUs are single GPUs here, which is 5090 is one of the best GPUs right now you can get your hands on, if you can even. It's 1040, 1 equal flops per second, and this scale is obviously on 14-point operations, not on second. But if you divide this number by this, the Gemini Multitemporal will take about 300,000 years to train on 5090 to put things in context. So the point being, systems to tie this into HPC, we need to build and experiment with these models. Infrastructure is key, and data pipelines are key, and HPC and knowledge on HPC systems and cloud systems are crucial. And hopefully within this summer school you'll learn some of the terms and some infrastructure on what they are and how to leverage them, and hopefully you take away some things from this summer school. So plan for today is we talk about foundation model for science. We'll talk a little bit deeper on Prithvi-EO for FM, and also some fundamentals to put context on towards the hands-on session. Then we'll have lunch between 1 and 2:30, and with the note that we need to have a couple of tasks running in the background so we can come back and not worry about waiting for something to finish. So after we come back, we'll talk about deployment and inference, and then hopefully we'll be done with everything by the break, and between 4 and 5, we'll see if there's anything remaining, we'll try to do that. If not, we'll do an open discussion and a feedback session. So that will wrap up for today. So, final takeaway, I want to leverage FM to enhance the research process, develop a strong understanding of geospatial foundation models, practically apply a fine-tuned geospatial model, establish a data science environment and conduct analysis. We also want to understand utility of cloud computing in this day for AI lifecycle for operational deployment. We also hope you learned something new, something you didn't know that you came here for, and that will challenge you to go back home and learn more. meet meet a potential collaborator and some new opportunities. You also feel listened to here, and you have a good time. Right. Thank you. Any questions on this part of the presentation?
I don't have. Okay, so since you mentioned domain experts in your slide, and I agree that they're always important, how would you strike a balance when you sort of provide insights to the community between what domain experts can actually tell you and benchmarks like Pangea or GeoBench can inform? So how do you see these? Are they complementary? Are they two different things? Are they the same?
So I can speak a little bit about it. Don't expect a really comprehensive answer from me. So the way we approach domain experts is, when at least in building these foundation models, is even before we do any architectural decision, we do a meeting with all the domain experts and discuss what's the data, why do you need a foundation model in your field in the first place? What's the data assimilation? What's the data problem that you have? Why is it hard in your field to have a fragmented data system, and why there is a need for a foundation model? First, understand that, because that will inform the downstream, the modeling, the dependence, the data priors to understand, and the model biases to apply to map to the data priors that we have, in a sense. For example, weather FM, the underlying governing system is a system of Navier-Stokes equations. And we can obviously do some CNN, basic CNN blocks, and get away with some predictions, because it's a stochastic model, will of course work. But doing that using appropriate convolutional, using appropriate blocks that will be better suited for solving PDEs is going to give a more explainable model that we see in the results. And that insight will be given from the domain experts. That won't be given by benchmarks and things like that. So that's the kind of science-backed interaction and science-backed model prior information that we want to leverage to inform the model biases and tie that together.
Yeah. Oh, very good, thanks. It's a sort of co-design approach or something.
Yes.
Yeah, thanks.
I have a question. Why is the HDCRS dataset 30 meters
we are trying for 10. I think it would be safe for me to say we are not confident enough in putting an archive for 10, because apart from science reasons, there is also data storage requirement reasons. We need to justify the storage cost, because it's not just 3x more, it will be more. So justification of that compared to the downstream applications is needed. Any questions? If not, I will move on to the next one. Right. So the next few minutes, we'll talk about a little bit of a deep dive into the Prithvi Earth observation model. It's a foundation model on the built on top of the Harmonized Landsat satellite, Harmonized Landsat Sentinel data, and it's a version 2.0, which is different from the 1.0 in the sense that it's multitemporal. It has a contextual understanding of location as well as time is the main difference between 1.0 and 2.0. The presentation slides are based out of slides from Dr. Sujit, who is the lead AI researcher and the lead for the foundation model group in Impact. He's also one of the committee members in the GRSS Earth Science Informatics Technical Committee, and specifically he leads a group called Earth Square, Earth 2 or Earth Square. I will be presenting this as well. So again, the same thing, the motivation foundation model, which is exacerbated by 1 billion petabytes worth of data for NASA because of the multitude of observational systems that we have. It's virtually not, it's not feasible for us to label data products from each of these observational systems if we are to do that. And obviously we would there is a community behind each of these systems as well, which would need to cater for, and that's not a very scalable system. We are relying on supervised machine learning, and we need something to solve the gap of labeled data, of course, which is why we want to explore foundation models as a strategic area AI development. I think I will skip this slide for now, but the takeaway is we worked on improving Prithvi with a multi-temporal aspect of it. The improvements are multi-pronged. The improvements were not just on the architectural level, which the architectural improvements are majorly adding the temporal aspect. It has more idea of what the previous time steps are in context to what the current input is. So it can, if we can add two more inputs to the model, and it will understand contextually what the progression is. And the progression itself, what we add to the model itself is not really fixed. We can add the last two observations, we can add last 2 months observations, and it will contextually understand. Obviously, we need to provide the context as well, but the point is that multi-temporal aspect is not fixed to a fixed window. We can change the window as well, that's the point. It also knows location information by the way of encoding location into the model. So we'll talk about how we encode it a little later. So these are core architectural augmentations to the main one, but there's also other improvements like data sampling and model size improvements as well. The model showed some improvements in basically all the downstream compared to the Prithvi-1, of course, but also at the time of publication, other existing foundation models as well. So, in the stack is as follows. We have from the data source, we have sampling and filtering and pre-processing and self-supervised learning method, which then goes into the encoder-decoder foundation model architecture, and then to the output. In the sampling, we incorporate for the 2.0 some data diversity. We make sure the model is not just overfitting some similar data. Some data diversity practices are incorporated. We'll talk about a little bit more later. Data quality requirements are there. We throw out data that doesn't meet our requirements. We'll talk about filtering that was applied. Model architecture and hyperparameter selection. Just talked about that. We use ZAR, it's just a efficient data format to capture which we used to train it on a large scale. On the fine-tuning side, just provide the task-specific label data and type of tasks and type of parameters, and do it supervised learning. So this is the third paradigm for the foundation model, not the first two here. Then these weights will be transferred on the inference side. We just provide the location and time, and the weights from supervised learning is transferred, and we do that's the overall system. The point here is we are not just building one model and publishing it. We are building the full stack, and each of them, including the models and the services, is either already out or in the process of being worked on and will be open source soon enough. Okay, we talked about this briefly too in the previous slide, but Harmonious Landsat's Sentinel reflectance data product is a total of 15 thermal infrared bands, and it has a global land coverage, 2 to 3, I think it's 4, 2 to 4 days observations. It's a high spatial resolution, 30 meter per pixel resolution. We have two data products here that are combined, L30 and S30, GeoTooth file format, internally represented as ZAR for optimization purposes, but GeoTooth is what we use. The tile size, each tile is 3660 by 3660 pixels is what we get the data product as, and the temporal coverage starts from 2013 onwards. One thing is, although there are 15 visual and thermal bands here, we are not using all 15 of them. We are only using 6 of them here due to compute and requirement considerations. The visual blue, green, red bands, the near infrared, the shortwave infrared 1 and shortwave infrared 2, and those are the 6 bands to ensure consistency between the two L30 and S30 bands as well. On the pre-processing preparation side, we did a cloud filtering to remove NAN issues. We did only kept any tile that had less than 15% cloud coverage, NAN per tile, no data values, less than 5% is being kept. So we also did diverse land use and land cover ecosystems. So the way that was done is a few things. We did Copernicus land cover and resolved ecoregions data. So this data has about let's see, around 800 or so regions, and we made sure we sampled equally across these regions to make sure all of these different climatic regions are covered to ensure that the model is representing all of these regions equally. And we also made sure the urban areas, which are sparse in nature, was also oversampled as well. So to put that in context, we ended up, finally we ended up with 3028 or training tiles and around 170, 160, 170 validation tiles. And out of that, around 1,000 of them are urban area tiles. Yeah, and to also put the sampling and climatic conditions in context, lot of, if you're doing a sampling, a lot of them would end up being C. So this sampling makes sure we capture what we are interested in, what our downstream would be useful for. So you can see how the sampling occurred, and you can see the coverage in terms of samples, the training and validation data, where the training and validation data set is from. The blue represents validation, and from red to green represents training, and sampling frequency as well. On the distribution side, we have two charts here. One represents the year and the count. The green represents training samples, and the blue represents validation samples. The chart on the left is pretty self-explanatory. The chart on the right is more valuable here. What it says is, when we take one sample, we obviously take, since it's multitemporal, it's a stack of samples. And between the timestamps, this represents the delta between the timestamps. And we make sure it's not just one specified delta between the timestamps, it's a wide, like a range of delta. And anywhere, we take timestamps anywhere between 0 and 25, and that's the distribution that you see here. And we deliberately make sure that this is a wide range of timestamps and split between training and validation. Also make sure that there is a dropout condition in which we don't provide any timestamp to the models too, because there could be times in which we don't know what the timestamp is, and we don't want the model to learn and over-train on over-rely on the timestamps. We want the model to be less reliant on the timestamps as well. And we also hide the timestamps when and let the model learn as well as a strategy, training strategy. And this is the architecture. It's the architecture, the core architecture itself is not too different, but the main difference being it's multi-temporal now. So we have stacks of input images, and which is getting flattened. And we have the main core architectural change is the 3D patch embedding and 3D position embedding here. So the patch embedding, the standard MAE, the architecture itself is a standard mass data encoder. The input image of the first input image is divided into patches. It's a large portion of this patches is randomly masked. I think the ratio is 78% masked and 25% kept. And the decoder is supposed to predict the hidden 78% as a strategy. The spatio-temporal adaptation here is based on the positional encoding here. So to handle the time series, the input is divided into the patch embedding will inform the positional encoding will inform the spatial aspect of it. So we'll know, the model will have an idea of which patch, which temporal aspect, which temporal data the patch contributes to. The location here is not passed through the positional patches because we don't want to provide the location, which is like latitude, longitude coordinates as the input to the model. It was rather passed as the bias to the model, which was an architectural decision that was made rather than just passing it as an input to the model. One other consideration here is that this had a convolutional bar with the channel convolution size as 1. Any idea why the channel convolution size was 1? Because in VIT, if you see channel convolution size won't be 1. Because it's very counterintuitive to have that. So, the reason here is, unlike a video where between each time frame, they would be sharing a lot of information between each time frame. Having a bigger channel convolution means they are going to, we are assuming there will be a lot of common features that they are going to convolve together, and there will be there will be a wealth of features that are combined together. In this case, we cannot assume so. Between image now and the image 1 month before, they are going to have huge variability potentially, and we don't want to convolve those together and lose potentially a lot of information between them, which is why the convolution was 1. Moving forward, again, like I said, 3,000 tiles, 4.2 million samples for training, and 45,000 samples for validation. Once the tiles are processed, and once we do like rolling window of patches, samples that we sampled from the tiles, we ended up with 4.2 million training samples and 45,000 validation samples. Training was done on ANDREDs with 40 GB memory, 4 GPUs per node, pre-training on 80 GPUs, and ran for about 11 days. The 300 million parameter and 600 million parameter models are available on Hugging Face. One quick note is that we have 300 million parameter, 600 million parameter, and 300 million parameter with temporal and locational embeddings, like the patch encodings with temporal attention, and the location data being infused within the metadata of the bias as separate models. So we have 4 different models: 300, 600 million, normal without any of the previous architectural changes, and 300 million, 600 million with temporal and location information being trained. So 4 different models, and you can see, go to this link and download them. Just the training loss. Overall, they look to be pretty smooth. Just indicates the MAE strategy was pretty smooth, and the model went into saturation. Right, shifting towards downstream and applications, we tested on a few applications, focusing on segmentation, regression, and we also did some generative applications as well on the segmentation. We did burn scar detection, which we'll be doing a hands-on for today. Floodwater delineation, land site classification, land site detection, multi-class crop classification, and burn intensity estimation. On the regression model, we did a multi-data fusion GPP flux. So we'll talk a little about it too. All right, on the fine tuning, it's a pretty standard approach. Stacked images of the multi-temporal event of the burn scar event, passing it onto the encoder, upsample the layers. So there is a segmentation edge, and from the segmentation edge, we use a cross entropy loss to learn the segmentation mask of where the burn scar is. For crop classification, it was stacked timestamp of images. Similar strategy here, with multi-temporal here, and this is also a similar strategy. The model can do single as well as multi-temporal as well, without too much modification. Some metrics. The geobench and segment class on the geobench is widely cited and used benchmark out there. Rocco was also talking about it briefly some time back. It has, I believe, 6 classification tasks and 6 segmentation tasks, if I'm not wrong. And Prithvi at the time of publication did well overall. And one thing that we noticed is on the architectural improvements between 1 and 2. So just taking Prithvi-EO 1 and Prithvi-EO 2, just 100 million parameters, right? Between just these two, there was a 2% increment. Just by changing these two only differs by the sampling strategy. So just by changing the sampling strategy, we saw improvement, a consistent improvement in segmentation tasks. And between 100 million and 300 million, there was some increase, but the real increase is between the EO 300 million and the 600 million, about 3% increase, and that defines the scale. And adding temporal and location information for geobench segmentation tasks had maybe only 1%, I would say, increase in tasks, which may or may not say much because we need tasks that are specifically that can specifically leverage location and time information, which may or may not be the case in geobench segmentation. So 1% may not be indicative of how useful PL is here. Okay, so some numerical results here on the SEN 1 plus data sets. You can see on the MIOU, I have some observations noted. Like a 3.5 to 4 point improvement over EO 1.0 on the flood mapping, and 7 point improvement over 1.2 in the burn scar mapping overall for both tasks. The fine-tuned model was used with the backbone or the decoder head for the segmentation, used UPerNet model here. And these are some examples of the predictions, and just visual inspection looks to be like coinciding with what the ground truth is. Fairly loose is a little bit of high level like a resolution, but overall it looks to be closer to what the original is in terms of intersection. On the landslide detection, which is also a segmentation data set, we did some ablation study on, not here, but in the next slide. On in the next slide, we did some ablation study on land cover classification, just holding out some fraction of data set, just to see how it performs when on lesser amount of data. So BAVAT is the SEN4 map is the land cover classification data, which was the benchmark that was released with the paper, and Prithvi-EO 2.0 did so the full data did a little better, about 3.2% better on the BAVAT data, but going all the way down to just 6% of the data. The model comparatively did about 7 to 8 points better than the AAT. So it kind of points to generalization of Prithvi because of the the pre-training strategy here. On the crop classification, so it's just a inferencing of the crop classification that we just spoke about. So GPP flux, GPP is gross primary production. It's a key climate variable. It's a regression task. It's the way this was done is not in a traditional sense, in the sense that we used Prithvi encoder decoder as part of encoding of the HLS image, and this was fused and concatenated with MERA2, which is only 10 variables of MERA2 centered around the covariance flux towers. These are like in situ observation towers. And these values are fused along with the HLS image of that region, which was passed to the Prithvi encoder decoder, and those embeddings are frozen and a linear layer is applied, and then used and regressed using a NC loss. One observation here is that when we did the validation, we observed that the model significantly outperformed a standard random forest baseline. And the random forest baseline used a lot more variables than just just what we used. So it indicates, so for example, it used handcrafted vegetation index data, which can directly, which is found to have a high correlation to gross primary production data. So just by using HLS as an encoder, as a feature selection strategy here, because it's frozen here, it's not, we are not using it for training. We can see its usefulness as being a feature extractor for satellite imagery to provide more added feature inputs to a particular region and for tasks like regression and so on. And you can see how it can be used for, if you can store the features on a database, you can use that and for retrieval and use that for computing and similarity search and so on. And this is the result for the same task. So the true GDP also has, it's very close in terms of R2 between the true GPP and the predicted GPP. Obviously, the training set is much closer, and the test set has a little bit of variance, but overall pretty close. So as a summary, we did some train the geospatial FM on HLS. HLS also made some improvements, and this model was right on time to incorporate those improvements. Sampling strategy was based on land cover, land use, and temporal conditions. 300 parameter model, temporal with and without temporal and location embedding. 600 parameter model with and without location embedding. It was being evaluated on multiple downstream tasks and found to have some generalization capabilities. It was only trained on small data set studies, not on a few shot or a single shot level, which could be a future avenue to explore. So you can scan these and go to models and data sets, and if you're interested, and scan the other one for the paper and more details if you're interested. I will leave the other page for a little bit now, but I want to thank all the collaborators here, NASA, IBM, ULIC, and Clark University, UH, and Arizona State, and USRA. So it's a collaborative effort between multiple universities and research institutes. So I'll leave it here, and I will take any questions that I can answer. If not, I will pass it on to people who worked on it. Okay, let's get started with the next part of the theory. This is mostly focused on talking about AWS SageMaker, some fundamentals. Ideally, we should have led with this for day 3 and day 4 as well, to give some context into why we are doing what we were doing starting yesterday. But as you can see, there were a lot to cover yesterday, and JJ wasn't able to make today happen, so we had to shift the program a little bit. So we'll talk about SageMaker a little bit today, and why we are doing the way it's set up on day 3 and day 4. So I don't think I need to introduce AWS. We all know how it works. I guess more importantly, you would know when it doesn't work, because most of the infrastructure in the internet basically relies on AWS in the backend, like Twitch, Amazon, obviously, Facebook, a lot of services, a lot of universities actually. I remember I was a student when this happened, and our classes, online classes, infrastructure, a lot of the services went offline, and it was also during COVID as well, and we couldn't do much both at work, also because GitHub was also down. So again, it shows how powerful AWS is. Talk about monopoly, which we can't do anything about. So one thing I want to highlight is AWS is not just AWS is a complex. Oops. Let me try and make this a little bigger. So AWS is a complex system of components. We have a set of compute, EC2 instances, which is your compute. We have storage solutions, databases, we have networking solutions, application services, deployment and management, monitoring. So everything that we need to manage a connected system and a web service and so on. So and it's also documented and standardized. The idea is with this and with proper utility, you can stay within this system and get a lot of things done by just utilizing the system. And also, these are fairly generalized enough that you don't have to really tie into this ecosystem. You can obviously also use similar offerings that are existing out there, but I would say currently AWS is the most prevalently used cloud service provider right now. So they also have what they call AI stack. So that involves tying their infrastructure together, which is a CPU, GPU infrastructure, with prevalent frameworks, tightly coupled frameworks, which are existing infrastructure like PyTorch, TensorFlow, and so on. And they couple that with their EC2 instances, their interfaces, and they make it available to their platforms and services, one of which is we'll be talking about more, which is AWS SageMaker. And they have other services that are built on top of it, which is recognition, translate, comprehend. These are like service offerings that AWS has that you can use to applications that we can use as an end user, right? So that's their AWS AI stack that they are offering. It's a little outdated. There's a lot more offerings right now, but just to give you an idea of how their infrastructure is layered within AWS. So talking a little bit more on AWS SageMaker, it's a fully managed service intended to enable data scientists and developers to build ML models and applications into a production application. So buzzword for this is ML Ops, ML operation. And they claim to tackle the four core tenets: end-to-end machine learning platform, zero setup required, flexible model training, pay by the second, which they honor with varying capability, I would say. So on the zero setup front, what they claim to provide is integrated Jupyter notebook or notebook instances and as well as other instances. So essentially, they have tightly coupled notebook instances that can that has pre-installed deep learning packages that are tightly coupled to their hardware, which are enabled, which are deep learning and high compute deep research packages compatibility enabled. And they have access to rich open source frameworks and tools, and also the hardware also supports it. Cons is it's not exactly zero setup. You need to have some familiarity with AWS. It's a buzzword, I would say. It can also get pretty expensive depending on how you use it and depending on how, if you're not going to do some due diligence, which is not exactly well documented. So that whole consideration need to be done. On the flexible model training front, they offer out-of-the-box models that we can directly port into the system. They have some core support for TensorFlow and things like that, which we don't. If you've done TensorFlow PyTorch in your own hardware, you know maintaining them and making support with them with the dynamic hardware ecosystem and dynamically changing system is a pain. And they manage it for you by and just removing them and just providing you a system that just works is can be useful. And they also maintain a repository of models that works, and you can choose without worrying about wrangling data, whatever model that you can choose. And there's also ways that you can choose do multiple models and see which one is best within the system without much choosing. So geared towards people who just want, who can just spend money and want the best models or combination of best models available. So that's flexible model training. And we can also bring our own models, which is what we are doing in today's workshop. So on the managed training, they also manage the training run models. So what that means is you might have seen this piece of code that you ran yesterday. So what this is that you must have run this estimator that points to an SP URL, which points to a model path, the output path, the name of the job, and the input mode, and so on. And that connects to your S3, where the path of the model is, where the output file should be, and checkpoint destination is, so on. And that connection will create a training instance in the background. Obviously, you will need to define what stopping conditions are and so on. But the point is, it will create a training instance, automatically run it in the background for you, and will stop the system when the conditions are met and shut down the system. The model can be, like I said, something you can just define as a list of models that is available out there, or you can also provide your own model as well. And that's what managed training run is. On the model deployment part, so this is what we've covered so far is a data scientist, ML, like expert job, right? This what covers after is ML engineer or developer's job of deploying the model to a service that should be scalable, that is also conducive to testing, guaranteeing certain latency requirements, throughput requirements, and obviously custom model support and development kits in Python, JavaScript, and so on. So the developers are free to use whichever way they want. Going from a trained model to here is pretty straightforward, like we will be seeing in the later part of the hands-on today. So how all these make sense for today is this for both day 3 and day 4, we employ SageMaker and we use managed training notebook that each one of you have access to, which has pre-installed packages that you need. Obviously, those were installed by us, not by SageMaker themselves, but we started with instance that had immediate support with PyTorch and other packages to begin with. So we installed only the packages that were needed for our custom model. If we are going with a generic model that didn't need it, we didn't have to install it, right? So again, the training notebook defines the free data and the custom model and how to connect to that and all that. And we trigger the training job, which runs in the backend and background, and the S3 bucket holds all the artifacts like model training and the configuration files that is needed for the custom model. The Hugging Face holds the data sets and the initial weights that is needed by the model. And the ECR registry is, you can think of it as like a managed EC2 Dockerization, which is what the training job uses. You can think of it as a way the SageMaker training brings up an instance to run a model and shuts down the instance when it thinks like it meets the stopping condition, and that's the registry that it uses. So all of this is encapsulated under the SageMaker Studio Lab, which is if you remember from yesterday, that is your initial login page where you go and click create your training notebook and monitor your training runs and so on. So that's your main Studio Lab interface where you can monitor your deployments, training runs, create notebooks, and so on. So that's your entry point. So that's some context into the setup, and we will move forward with the training with the hands-on. Unless you have any questions, so I'll wait for the questions, then we'll move on with hands-on after this. Questions on SageMaker specifically? Yeah.
So I have the question that we upload our data to S3 all the time, yeah? So can't we use the local memory of SageMaker?
You can. I guess that defeats the purpose of managed instance, right? So your notebook is essentially for you to understand the data and like start a training run. If you are going to use a local notebook, that also means you are going to use that notebook instance to train the model to, which is counter, it's not efficient, right? You're going to have the notebook instance run the model, and the whole point of creating an instance is like you don't have to worry about like managing your notebook and shutting it down whenever it finishes. Like you're offloading it to a managed training job, and it could be like multiple managed training jobs too, right?
No, what I mean to say is that every time we run the model, it just every time first we download the data into our local instance, then we upload it to S3.
Yeah.
Then the model loads it from the S3.
Yeah.
So instead of we do three, like it's like we're increasing the time by uploading it and then downloading it.
Yeah.
So if we do not upload it, then we have it locally, we just use it. Shouldn't work.
I would argue what we are doing now is the more time-consuming, less efficient one. We should do it like that. The straightforward way to do it is to upload it directly to S3 and point it there, rather than us downloading it to the notebook.
Yeah.
And like that's just to see, like tangibly see what we are downloading and where we are downloading it from.
So it's download once and then use it forever.
Yeah, just point the SageMaker instance to where the data is, and just upload the configuration directly to S3.
Then there is one more limitation that I've faced.
Mm-hmm.
Is that the maximum time of notebook is 180 minutes. So if you have to run a model and you have to go somewhere.
I don't know if that's a limitation that we put upon ourselves, or is that a?
It's defined by SageMaker.
Oh, really?
Yeah.
Oh, then we shouldn't be using SageMaker for training a model anyway.
Yeah.
Right.
It's like the best way to use it. We do ECR, and then we just train it using Airflow.
Yeah.
But if we do it in the notebook after 3 hours.
Yeah. That's good to know. I didn't know that.
Yeah, I faced it.
Okay. Okay, so the intention was never to train a model with using SageMaker, just to, okay, that's good. All right. Any questions? All right, thank you. If not, I think we'll move on to the hands-on session for today. So between now and lunch, I'm hoping we'll cover fine-tuning of the HLS foundation model, and while we are at lunch, I'm hoping we will trigger the training job and it will run in the background. And when we are back, our jobs will be finished, and hopefully it doesn't error out, and we'll continue with the next part. Ideal case. Obviously, it won't be the ideal case, but we'll see. All right. Right. I would recommend starting with the summer school, the GitHub repository that we used from yesterday. And also, I'm hoping you guys have the credentials with you from yesterday as well. If you don't, please let me know. I can send you, but I need your, and just send me your name and I can send you the credentials if you don't have your credentials. So let's go to login, put your username password again. go to Jupyter Lab and open your existing running instance. So, is everybody on the notebook? So I would recommend as a first step, go to the terminal, since a few of you had an older version of the repository. Be careful with this command. But I would do this. Oops. RM space hyphen RF space HDCRS hyphen school hyphen 2025.
Your share screen, you drop out.
Oof. How did I not? So I just want to clear everything that you have in your repository and start pull all the new updates and work with a fresh copy of the repository. Also, before doing that, make sure you've closed all the existing notebooks that are open, because if you have them open and pull the repository, it's going to, the older snapshot is going to overwrite your newer ones. So.
You make it a little bit bigger, I think.
Yeah, I can do that.
Thank you.
So that should clear all your files from yesterday. Then I would click on Git, Git clone repo, and I will copy the repository name from here and paste it here. I think that should work. Let's see. All right, that worked. Once you've done that, this should hopefully have the latest repository changes too. Then you can go to notebooks and Prithvi-EO notebooks and fine tuning.
Which we
It's the same one from yesterday. HDCRS-school-2025. Let me also put this in Slack. Cool. Again, just going through some basic things. In what this notebook will cover is the fine tuning for the Prithvi-EO version 2.0. So essentially, transfer learning. We pull the base model, download the fine tuning weights, fine tuning data set, and create a training job that uses the data set and fine tunes on the base model. On the technical level, we are going through how AWS SageMaker model training is intended to be set up. Hugging Face datasets for machine learning workflows, some basic training parameters, and deploying the fine-tuned models, at least within the concept within the SageMaker framework. On application level, we are going to do burn scar detection today using HLS satellite imagery. Burn scar detection, it's this crucial environmental use case for monitoring, climate research, policy making, and so on. So it's very visible in the 30-meter resolution as a patch of burnt area, and it could be caused by multiple like forest fires, man-made fires, lots of different reasons, but the scarring is visible, and we can use that as a use that as a way to monitor several high-value use cases. Yeah, we covered all this, so I'll skip this. On the Prithvi-EO, like I said, we have 100 million, 300 million, 600 million parameters model. You can just change the name in the Hugging Face repository and download the model that you want. It has a TL and models which indicates it knows temporal and spatial understanding for EO tasks. And it can be fine-tuned for various geospatial applications. And there is a specific way that you need to do for fine-tuning, which we'll get to in some time, in a bit. So before running any cell, we need to change the kernel to Prithvi-EO. So if it's not set for you, go to kernel and choose Prithvi-EO and select, and also restart. Briefly talking about the libraries that we are going to use, Boto 3 is the Python library that we are using to interface with AWS components. Can interface with basically anything that we saw on the first slide of the presentation, like S3, EC2, that this provides you a Pythonic interface to interface with them. There's a SageMaker interface as well that we are going to use to model training, to start a model training job and deployment job and so on. And then there is Raster.io, which most of you in the geospatial community will be familiar with. It's one of the most famous libraries to read and process satellite imagery. Hugging Face, it's the predominant ML model and dataset repository right now. We are going to specifically use Hugging Face Hub, which is a way to access models and datasets by using their reserved names, and we can provide the names and download their model weights and datasets from the hub. And then there is a snapshot download, which is used to download and like the model files from the Hugging Face. The difference between Hugging Face Hub and the snapshot is that you can do a more targeted download with the snapshot download rather than Hugging Face Hub is the more overarching interface. HF Hub download is more like more specific files from the repository. It's like more like low-level download. Again, the reason to use this is Rastreo for NumPy for data handling, Bodo 3 SageMaker for infrastructure management. Configuration will be managed by YAML files. Yeah, it's just a file format to manage configurations. And the datasets will be downloaded from the Hugging Face Hub. So we will import all the libraries that we need. Don't worry about the warning. Hopefully, you won't have any problem importing any library. Is something good? Okay. All right. So just next step is dataset preparation. Again, Prithvi-EO is based on HLS data, specifically Landsat 8 and 9, 30-meter resolution. Okay, this is what I was missing. 16-day revisit cycle for Landsat 8 and 9, and 5-day revisit cycle for Sentinel-2. Landsat 8 and 9 is 30-meter resolution, and Sentinel-2 is 10 to 20-meter resolution. So the reason to combine them is obviously we can do more frequent observations for detections and so on, and consistent data format, one way to access both of them rather than dealing with two different repositories, and also has a better coverage because both are staggered coverages, so two is better than one. The dataset that we are going to use is specifically burn scar dataset. We had SMEs label a few burn scars based on known events. Again, 3 different samples, typically a typical ML stratification here. On the data structure, the foundation model Prithvi 2.0 understands 6 bands: blue, green, red, near infrared, shortwave 1, shortwave 2. The labels themselves are just binary masks, segmentation masks of burn scar, yes or no. The metadata has location, date, and acquisition parameters, which should be used by the model. Hugging Face datasets is we publish everything in Hugging Face because predominantly it's what's being used by the ML community now. So, all right. Moving on to dataset download, just run the snapshot download. We provide the repository ID. The allow patterns will just download the patterns that match .gc. This should be the only pattern that match in the dataset, if I remember. But it will only download the patterns that match this. The type of the repos, the dataset, and you can provide where you want to download it. You can also provide the cache if there is one cache file. And this is just a command to extract that compressed file format into a folder. So that should take a few moments. And this is our typical dataset structure that we'll be downloading it into. So it's a 512 by 512 tile. Each image is a subset of HLS, which is a 512 by 512 tile. And we have mask as well as the mask as a TIFF file, as well as the merge, the actual 6 bands merged into one file as a TIFF file as well. was quick. So I think we should make sure that the data downloaded as intended. Okay. All right, for this test, I think we are going to use validation images as test images, which is not the best practice. But ideally, you'd want to use a separate split of validation. I think we all know why. We would want to use a different test split than validation. But for demo purposes, we are going to just use validation images here. So similar case then, like yesterday, make sure you use the bucket name that is provided to you from yesterday. I'm going to use mine, but you should have yours. So we are going to upload the data to S3 here. Let me just run the cell and then let it upload and then go back to what's happening. So again, S3, it's a region agnostic storage system. So a training job can access this data from anywhere. So ideally, you can have your S3 data from anywhere. Anyone can upload it and maintain it, and your training job can point to it and use it for use it. Yeah, cost effective. It's cheaper than some other alternatives. It's also like tightly integrated with SageMaker training. There are other ways SageMaker can use other training sources, but S3 is probably the easiest way to integrate training data. What we're doing here is to create a SageMaker session. We start a SageMaker session by just using session like so. Create a upload data and just provide the path of where it is, where our path is, bucket name, and so on. Simple signature to upload the data. And we are just creating 3 different upload data calls to transfer images from whatever is downloaded from Hugging Face to the buckets. Hopefully that's smooth for you guys and you don't have any difficulty on uploading it. Oh, that's a network operation, so that's going to take a while. So while that takes some time, I think we will go through some configuration things. Let's actually open the configuration file, right? let's open burn scars configuration. So this is the YAML file that if you even use TerraTorch, you should be familiar with this. This is just a way you define the trainer, the devices, the batch size, number of workers, the dataset bands. This mapping is important because this defines the order in which your data is being called. And in the data as well as in the output, this is how you are presenting in the data the order, and on the output as in the input to the model, what the model input is. RGB indices is how it needs to be mapped to produce RGB visualizable index. The means and standard deviations are calculated in the next cell. We'll talk a little bit more, but this is to make sure that the model learns properly, and we'll talk a little more. These are all model configurations, transformations that we can define. More documentation is in the TerraTorch. This is based on the TerraTorch library. And we have this configuration as part of the repository, which we'll need to upload as well. So again, we'll read the config here. So since we downloaded some statistics, since we downloaded data for burn scars, if you are going to use your own fine-tuning data set, it's important to calculate some statistics about your data, and that's essentially to normalize your input data to make sure the training is stable and converges better. This would make sure that your mean and standard deviation, mean is 0 and standard deviation is 1. We are doing essentially what's called z-score normalization for the data at hand, the fine-tuning data at hand. So the code is here, and we are just loading the image directory and using NumPy library and standard operations to calculate means and standard deviations. And reading, we'll be putting it in the configuration ideally. Please raise your hand if you have any questions, and I can help. All right. Some training configuration that is needed for the training job. So in the next cell, I'll come back to the markdown here, but there is identifier, use case. Make sure that you have an identifier that you can remember, maybe workshop and your ID or your name, but also make sure you note down a time or something. Say if you run multiple jobs, you need to make sure that you know when you triggered it too, right? So make sure you put an identifier that can uniquely identify your training run, because this is an identifier for your training job. And your use case will indicate what the model is. So this can be burn scars too. This is fine.
This one cannot have an underscore, right? Or
Yes, please, no underscore. Yeah. Yeah. Yeah, the rest you can leave as is, should be fine. Okay. I think we spoke on the backbone, but you should be able to, if you want to experiment with backbones, feel free to go ahead and experiment with backbone. For demo's sake, just do one backbone for now, at least between now and lunch. But if you want to experiment with how they work and what the performance is, you can start multiple runs, maybe after the duration of the hands-on. And just to give an overview, you have 100, 300, 600, and there is TL versions of it, which has the temporal and location embeddings as part of the model training as well. I think the rest is just typical ML epochs defines the number of epochs. This is the most important one here. For most of the fine-tuning job, there is a decoder, right, that is added after the encoder. And this specifies there are multiple transformer blocks in the decoder, and this specifies which transformer block that the output need to map to in the feature embedding space of the decoder. Essentially, it's either at the 1/4 or half of the 3/4 or the final depth of the backbone. So you can think of the decoder as having a scale to it. So it captures multi-scale information at multiple layers, at multiple transformers in the decoder layer. And where you attach your index, which index you attach your your data to matters here, because that is where your most of the information that your downstream task is related to will be captured. So there is a relation to which index that you're mapping to what your downstream scale is. So selection of indices also impact the architecture and parameter count of the decoder, and so it doesn't affect the backbone. It affects the decoder complexity and backbone. So the lower you go, the more parameters you would need to handle, and the higher in the neck, or the earlier in the neck you go, you would have lower parameters to interact with. Is the idea. So that is something to consider. Low level versus high level features to consider. So that's mostly the most I would say relatively esoteric thing about the configuration. The rest is just standard configuration and don't need too much explanation here. Right. With that out of the way, let's run this. All right. This one defines, I'm defining the backbone here, but I'm using the 300. For now, just use as is, but after the sense, you're free to use whatever you use. And we have a mapping for you right now that you can use. But again, depending on your use case, you should be able to play around with it and get different performances and different implications for it. Right. I'm just creating a config or using the config that I read initially, and just adding the arguments like the batch size and number of workers, number of classes to it, and also mentioning the backbone to it. So this is the configuration, which is similar to what Terra Torch would require. And obviously, since we are using the custom model, which is a TerraTorch model, this is the configuration that will directly be used by the TerraTorch model as well. Means and standard deviations that we calculated specifically for this downstream too, which we are adding it here. So taking the existing one, modifying it based on our requirement for this fine tune is essentially what's happening in these cells. All right, now that we've modified the configuration, what's the rest is just what we've done so far is took existing configuration, modified things as we want to fit our fine-tuning use case. Now we are going to use the configuration and tie it to trigger a SageMaker training job. So all we need is the config file, path, and the data URL. So essentially this. So config file, the model directory name, S3 URL. The role is this is just this is needed to make sure the SageMaker has an execution role, not a read or any other role. These are all just the things that it needs, the variables that it needs to get started with the training. I'm also defining an instance type that not the notebook, but the model will be trained on. So it's a P3 2x large, about 16 V100 GPU, 16 GB. So run this. Oops, I think I forgot to run this. Yeah. Okay. So once I've defined all the environment variables and the instance types, I'm going to start the estimator that's going to create this job for me. So let me start training job. And also, if you want to monitor what's happening, you can go back to the SageMaker UI and go to jobs and training. And you should be able to see your training jobs. And this is mine. Oops, someone used the same name as me. That's not mine. This is mine. Ideally, if we manage the visibility and manage the user access control properly, you shouldn't be able to see my run, right? So ideally, that would be the way. But since you can think of this as a collaborative training environment where it's fine if we see each other's jobs. So yeah, let's see. All right. You can also once the training job starts, actually, you can also find a little bit more verbose information if you go to logs. So, and look at what's happening more than just what's being shown here. Say if something fails, then you can see what's happening there. Any errors or failures so far? Yeah.
And also, I know that this stuff is run like over the 10 minutes.
No, as long as you see the dots moving forward, like new dots appearing, it should be fine.
Yeah.
Yeah, yeah, that's fine. Is it like what's showing here? Like, is it like downloading training image now, or is it
It's still downloading.
downloading what?
It's still like 10 minutes.
So you can see the status here, right? It started the training job. Then it was waiting for the capacity. It then prepared the instances, downloaded the input data. Now the training image was downloaded. And now the training is in progress. So it shows some. Yeah. What is it for you? So I just want to make just a quick comment that JJ was talking about layers of abstraction. As you can see, it's like a very abstracted system. For a research institute, this is not the most ideal system, I would say. But if you want to get something, if you have for like a startup environment or something, specifically for a quick deliverable, this has a lot of things that are built in and ready to go, well documented, that you can just get up and running and go to deployment without too much overhead. is when you would need this kind of a system is what I would think. Issues? Anybody still waiting for their training job to be started? Or did training job start for everyone? All right, perfect. Then I would recommend just run the next cell like so. And I think we will wait for it to complete and come back to hopefully finish trading job and continue with the next part. Also, we'll do one more thing just because we have some more time and we also want to see how deployment works as well. Let's go back to Terramind and notebooks. Sorry, not Terramind. Prithvi-EO notebooks, deploy and use. So not Terramind, but Prithvi-EO folder, notebooks and Terramind. Yeah.
I got an error by
Nice. Okay.
index until range.
Like. Or maybe Gurung file is correct. I'll just redoing the range of the change also change to Prithvi-EO. Okay, click on that. Yeah, change to Prithvi-EO. Select and restart the kernel. So for some reason, when you click the change the kernel, the current kernel still stays. Yeah, you can press that and it should execute it that way. Yeah, it should restart and
I see. Okay, thank you.
Right, let's open deploy and use .icynb. And one quick question before that: do you all have a fully finished training run from yesterday on Terramind? Anybody who don't have a Terramind fully finished training run? Yeah, really.
Start from the beginning.
Right. So that may, because what we are going to do now is deploy Terramine, because it takes 15 minutes or so. So we'll just deploy it, start the deployment, and we'll come back to a deployed instance, and we'll just go through it just to save some time. So hopefully you are in deploy and use notebook. Yeah, change to Prithvi-EO and restart the kernel. I have a quick question for you all. Do you know these names? We need these 4 names for you to deploy the Terramine model. The identifier, the model name, the configure name from yesterday. Yes? Yeah. So what we need to do is essentially this. Copy the file from fine tuning from before. So create a new cell and paste the cell here. Essentially, we want to export the variables from yesterday that you stored to deploy that model. So the identifier from is the identifier of your Terramine model, the model name, what the model name that you used. The config file name should be same. We can use the config file name from Terramine, but we just need to give the path, and the bucket name is your bucket name. If you fill all of that and use it, then we can use that variable name to deploy. We can follow this notebook to deploy your Terramine model. So if you don't know that, we can find it out. We just need to look it up on the S3 bucket that you submitted. Is the issue. If you know it, it's easy enough. Okay. Making things worse, we also purged your repository. Making things worse, we also purged your initial repository where you would have already had the file names too, right? So the Terramine configs is here. You should have used sen1 flux 11 config. So you could use that. So try and get the names, fill the names, and that defines your variable dot YAML. And that, if you have that variable dot YAML defined, that should deploy it. But if not, don't worry, we'll come back and deploy Terramine and at least Prithvi, because we will generate that YAML after the file runs anyway. So we'll do at least Prithvi deployment, and we'll see how we can deploy Terramine as well by tracing back the variable from your previous run. Who?
Is the point used notebook looks the same, so a little bit different. Yeah.
Oh no, I added the fact. So it goes like I created
So what's happening here is once the file finishes, you're just exporting a few things like identifier, model name, quantifier name.
We call them.
Just download, just store in these variables and then reusing it for deploying. So since we would have done this yesterday too, but we don't have it right now. But these identifiers can be found in your run. We need, if you know them, if you know what you've used, it's easy enough. If you don't, you can find a way to use your S3 and go to your S3 and then fill it up. Rerun this, so you will get a file now. And using the file as you go deploy. That's what for Prithvi, you will get the file anyway by running this. And we can deploy it after straightforward. For Termite, we need to find those variables for your specific instance that you ran yesterday and fill it. So ideally, you would have the file that makes in one run, right? So since between yesterday and today, since we lost the context between the nodes, we need to find the run, find what the model name is, and then put it there and deploy that. So find where the training flow is, find the model and find the configuration file name, use that name here, and then you can ideally you will deploy.
So like, probably some APIs can
Yeah. And this is for Prithvi-EO, whatever we're doing here.
Okay.
What I'm trying to do is deploy it yesterday.
But the same for both.
Yeah. Same code dog, but with Termite identifier that we used yesterday.
But the problem is that the training, it's before yesterday, it showed my name and my field. But now I can't find it. Yeah. From my it's really, I
I'm sure. I would say sorting by a patch. We love so that.
I have no idea. I tried.
Good.
But mine was completed, so maybe that's
But again. This is not. This is training. I think you should take training. That's what I find as well. Because training was
yesterday it was finished, and then I had my artifact.
we have some. We didn't reach that stage.
It was quite similar. I mean, it was fine, it was just
I suppose there is documentation.
yeah, that's what I was thinking. Okay.
You switch to the switch between these or because maybe if you are in the keyboard, maybe you can okay. Yeah, just switch You're saving 2 megabytes.
That's basically it.
And how many people are so you have some.
So Miguel has a solution if you want to use your deploy your Terramine. So you can find your model name by looking at your training instance. So if you are logged in, that is. So your model, your identifier is going to be just the first part before the SageMaker hyphen. Before there should be a hyphen before the SageMaker, and whatever is in the the name before the hyphen should be the identifier. So copy that. So I'm going to copy, let's say, the test data here. So that would be the identifier. I'm going to add that here as my identifier. And the model name should be, like Miguel pointed out from yesterday, that should be this. So, fire equals this data.
I might have to do one. I might that's the problem. Go for B2. Because I want to see it. Okay.
All right. Config file name
I mean, this is what okay. Just
is this. And bucket name is your bucket name. So let me copy this and send to you. This should work. So this should, if you use your identifier that you used from yesterday correctly, from fully executed model run, and I know some of you have executed model run but cannot find it, you might still be able to, if you know your identifier, your training job will still be valid. Just if you are not able to find a training job, you probably will have to restart the Terramine training job. Hopefully do that before lunch now. But you have the identifier, you have the model name, you have the config file name, and bucket name. You can export the values and variables. You can get the variable, and you should be able to follow this and start the deployment for Terramine. So, hopefully that is clear.
Word to rerun.
Yeah,
Functioning of Terramine.
it should be fine. You'd have that variable anyway. But if you want to do that, that's up to you.
I don't need to do that. Okay.
Yeah. This is if you want to not do that because you already have a valid run, you can just reuse the variables that you defined from yesterday and still deploy your old model.
Right. But that doesn't show up under jobs.
Yeah, if your model if your job finished job doesn't show up, then you need to run.
Is it possible to access the model through the buckets?
If you know your identifier, you can still try it, see what happens. It might not be just listed, but you can still, like, it's a still valid model that completed if you know it's completed, right? I don't see why SageMaker would just magically think that your model is not valid anymore, right?
Yeah, but even there is a possibility of
I'm not sure. I need to see why it's only showing me 50 results here and not more. And if you've deployed or if you want to come back and deploy too, that's fine. I think we can break for lunch too. I really don't see any requirement that says only 50 models are going to be saved. So there is no reason your model is not available. So just try with your identifier name and see if the model is still like your identifier that you used from yesterday, hopefully, if you know.
I don't know that identifier.
Okay. Yeah. Okay.
That's the main issue. I can find the
Yeah.
with the identifiers.
Yeah. Hmm.
That was a custom identifier. Right?
Yeah, yeah, yeah.
Yeah, I said something that like.
So I think some people are able to create TerraMind endpoints. I can see some endpoints already being deployed. Okay.
And how can we evaluate your training model?
Evaluate your trained model?
Yeah.
In terms of like metrics?
Yeah, we have 3 sets. Yeah.
So you've deployed, right? Once you, we will go through how you can infer from it. So evaluate is next step to infer, right? So I don't think we will cover evaluation like as in like a define a data set and evaluate comprehensively with IOE and all. We'll stop at infer, and evaluation is left to you because we have validation data set.
Okay.
Right?
But if there's a pipeline which automatically evaluates, so we have to write.
Yeah, you have to write because it's a custom model. But if you're using a predefined model, they will have evaluation scripts within AWS.
So you can access your bucket programmatically if you have your bucket here.
Yeah, you should be able to.
And so
Yeah.
you can find your
Yeah.
identifier from yesterday there.
Yeah, you can. Yeah, you can.
So
Also, in that piece of code, it's not saying the correct because afterwards it looks for TerraMind in the TerraMind.
Oh, okay. So,
I mean, what I did is
So this one will say within wherever this runs, which is EO, which is Prithvi. So I will just remove this. I'll just copy this here and paste it here. And not worry about this. Yeah, just make sure you're reading the variable that you just wrote to is what it is.
But she before finishing.
Because about the same way.
We have to go to the lunch, yeah.
Yeah, we can break for lunch, and if you deploy Terramine, fine. If not, that's also fine. We can come back and.
We come back in an hour more or less.
Yeah.
Because at the first night, more or less.
Problems.
Thank you. It's demonstrated that it's better that you are alone because more experience with you.
It means that you test a lot before proceeding.